Proceeding to our next topic of discussion, that is the elastic behavior or elastic performance of prestressed concrete beams or prestressed concrete flexural elements, as beams are primarily flexural elements, and when constructed with prestressed concrete, the prestressed concrete beams display a superior elastic behavior or elastic performance in the working range of loads, that is, the working stress range corresponding to working loads or service loads in comparison to the corresponding reinforced concrete beams. Therefore, in order to illustrate the elastic behavior or elastic performance of prestressed concrete beams, that is commonly abbreviated as PSC beams or PSC flexural elements, we will present the C-line concept or the pressure line concept, also known as the thrust line concept, that is traditionally the classical concept employed to demonstrate or illustrate the elastic behavior of the prestressed concrete beams or flexural elements. Starting with the definition of the C-line or the pressure line concept, the C-line or the pressure line is defined as the locus of the line of action of the internal compressive force resultant, denoted as capital C, of the internal normal stresses sigma x in the concrete along the span of the beam that are induced due to the combined action of the externally applied loads, represented by the set of external loads denoted as set Q, for a set of uniformly distributed loads or UDLs as well as a set of concentrated loads denoted as the set capital Q, and the internal pre-stressing force denoted as T subscript P in the pre-stressing steel. Based on the above definition of the C-line or the pressure line, the C-line can be mathematically or graphically obtained for a given prestressed concrete beam by applying statical equilibrium equations at various sections XX of the pre-stressed concrete beam. Noting that the statical equilibrium equations in case of beam elements or flexural elements comprise of two equations, that is sigma fx equal to 0, implying force equilibrium of the force resultants of the various stresses in the concrete and steel in case of the pre-stressed concrete beam are in equilibrium in the x direction or the longitudinal direction of the pre-stressed concrete beam, and two, the moment equilibrium equation sigma mzz equal to 0 with reference to the choice of coordinate axis selected in the solved example presented in one of the earlier lectures, implying that the summation of the bending moments about the z-axis, that is the axis out of the plane of the slide, equals to 0, implying moment equilibrium, that is the bending moments are in equilibrium about the z-axis. Proceeding further, the force equilibrium equation, that is equation number 1, requiring the force resultants of the stresses in the concrete and steel to be in equilibrium in the longitudinal x direction in the pre-stressed concrete beam, implies that the compressive force resultant or the force resultant of the internal compressive stresses or the internal normal stresses in the concrete at any location x or section xx should be balanced and therefore be equal and opposite to the tensile force in the pre-stressing steel denoted as Tp. Since the tensile force denoted as T subscript P in the pre-stressing force is largely constant, along the x-axis or at different locations x, the internal compressive force resultant, that is the force resultant of the internal normal stresses in the concrete, are also therefore constant along the x coordinates, and thus the argument x may be dropped from the notation of the compressive force resultant C in equation number 1. Additionally, the moment equilibrium equation, that is the statical equilibrium equation that represents the statical equilibrium among the bending moments about the z-axis, imply that the summation of all the bending moments sigma mzz due to the various force resultants of the internal stresses in the concrete and the pre-stressing force in the pre-stressing steel about the z-axis should equal 0. Referring to the definition of the C line or the pressure line, denoting the ordinate or the height of the C line, that is the locus of the line of action of the internal compressive force resultant C of the internal normal stresses sigma x in the concrete along the span of the beam due to the combined action of the externally applied concentrated and uniformly distributed loads, as well as the internal tensile pre-stressing force Tp in the pre-stressing steel, as y over bar x for any general location x along the coordinate axis x, that is the centroidal axis of the beam. Equation 2, therefore, that is the moment equilibrium equation number 2, implies that the bending moment due to the externally applied uniformly distributed load denoted as small q that is the external bending moment induced or generated by the externally applied uniformly distributed load Q and denoted as capital M subscript Z superscript Q at any location X should be balanced by the bending moments induced by the internal force resultants, that is the internal compressive force resultant in the concrete capital C, and the internal tensile force resultant capital T subscript P due to the pre-stressing force in the pre-stressing steel, resulting in the expanded form of the moment equilibrium equation, that is the statical equilibrium equation representing the statical equilibrium among the bending moments due to the externally applied uniformly distributed load and the internal compressive force resultant in the concrete C and the internal tensile force in the pre-stressing steel, that is capital T subscript P, as depicted by equation number 2, wherein the function E, the argument x, represents the eccentricity function, that is the eccentricity of the pre-stressing cable or the pre-stressing tendon with respect to the centroidal axis of the beam at any general location x, based on the sign convention that the eccentricity E at any location x is considered to be positive when the pre-stressing cable or the pre-stressing tendon with the pre-stressing force capital T subscript P is below the neutral axis in accordance with the normal or standard practice. The eccentricity function denoted as E with the argument x, representing the eccentricity of the pre-stressing cable or pre-stressing tendon at any general location x along the x-axis or x coordinates, is considered positive by sign convention when the eccentricity E at the general location x is below the neutral axis for the pre-stressing cable or the pre-stressing tendon. An example of a variable eccentricity function, that is an eccentricity function depicted as E with the argument x, thus signifying that the eccentricity of the pre-stressing cable below the centroidal axis of the pre-stressed concrete beam is a function of x. A parabolic cable profile may be considered for which the eccentricity function E with the argument x, in case of a pre-stressing cable or pre-stressing tendon profile with a parabolic shape, may be presented by a parabolic function, which we will elaborate on at a later stage in our discussion. As a special case, a straight pre-stressing cable profile or a straight pre-stressing tendon profile will be described by a constant value of the eccentricity function, that is, in case of a straight cable or straight pre-stressing tendon, the eccentricity function e with the argument x will be simply equal to constant that is depicted as e in the figure or the solved example presented in one of the earlier slides. Thus, proceeding with the solution of the two simultaneous linear algebraic equations presented by the force equilibrium equation and the moment equilibrium equation 1 and 2, substituting from equation 1 the value of the pre-stressing force or the internal tensile pre-stressing force in the pre-stressing steel, capital T subscript P, into equation number 2, that is the statical moment equilibrium equation. Presented in the expanded form here. The bending moment due to the externally applied uniformly distributed load Q, denoted as capital M subscript Z, superscript Q, where the subscript Z signifies that the bending moment is about the Z-axis based on the choice of coordinate axis illustrated in the solved example presented in one of the earlier slides, may be equated or related to the internal compressive forces at capital C by this equation. Alternatively, the externally applied bending moment, that is the external bending moment due to the externally applied uniformly distributed load Q, denoted as M subscript Z superscript Q at any general location X, can also be related to the internal tensile force due to the pre-stressing force in the pre-stressing steel. By substituting the value of the internal pre-stressing force, capital T subscript P, in the pre-stressing steel from equation number 1 to equation number 2, to arrive at an alternative relationship for the externally applied bending moment, also included in the rearranged and expanded form of equation number 2 after the substitution of the values from equation number 1. The physical significance or the physical relevance of equation number 2 relating the externally applied bending moment due to the external UDL or uniformly distributed load Q denoted as capital M subscript Z superscript Q at any general location to the internal compressive force resultant in the concrete C, as well as the internal tensile force resultant in the pre-stressed concrete beam due to the pre-stressing force capital T subscript P in the pre-stressing steel, is that the externally applied bending moment denoted as capital M subscript Z superscript Q about the Z-axis based on the choice of coordinate axis presented in the solved example in one of the earlier slides. Due to the externally applied uniformly distributed load, small q should be balanced by the internal resisting couple that is formed by the internal compressive force resultant denoted as capital C due to the internal normal stresses in the concrete, and the internal forces are internal tensile force resultant capital T subscript P due to the pre-stressing force Tp in the pre-stressing steel, since the externally applied bending moment capital M subscript Z superscript Q at any location and all locations X should be balanced by the internal resisting couple formed by the internal compressive force resultant C in the concrete and the internal tensile force resultant due to the pre-stressing force Tp in the steel at that location or cross section of the pre-stressed concrete beam. Based on this physical reasoning, for equation number 2 and defining a parameter A as a function of x denoted as A with the argument x that represents the internal lever arm of the internal resisting couple that is formed by the internal compressive force resultant C and the internal tensile force resultant Tp, where the internal lever arm denoted as A with the argument x at any general location x of the pre-stressed concrete beam is recognized as the sum of the eccentricity of the pre-stressing force Tp below the central axis at that general location x plus the ordinate or the height of the internal compressive force resultant of the internal normal stresses in the concrete, that is the C line above the central axis at the same location, cross section x, one can conclude that the externally applied bending moment denoted as capital M subscript Z superscript Q, where the subscript Z signifies that the bending moment is about the Z axis based on the choice of coordinate axes presented for the solved example in one of the earlier slides, while the superscript Q denotes the uniformly distributed load, that is the externally applied load that induces or generates the external bending moment M subscript Z superscript Q should be equal to and balanced by the internal resisting couple formed by the internal compressive forces resultant C in the concrete and the internal tensile forces resultant TP in the pre-stressing steel, thus resulting in a simple and a compact final statical equilibrium equation for the beam based on both the statical force and the moment equilibrium considerations, that is expressed in this last final line, which implies that the external bending moment M subscript Z superscript Q due to the external uniformly distributed load Q at any general location x or at any x coordinate of the beam should be equal to either and both of the internal resisting couples, or rather the internal resisting couple that can be expressed as either C times A at that general location x or TP times A at this general location x, where capital C denotes the internal compressive forces resultant in the concrete and capital T subscript P denotes the internal tensile forces resultant due to the pre-stressing force in the pre-stressing steel. And A as a function of x, denoted as A with argument x, represents the lever arm of the internal resisting couple that is formed by the internal compressive force resultant T and the internal tensile force resultant TP. Continuing with the salt example, which was presented in one of the earlier lectures with the figure depicting the pre-stressed concrete beam subjected to a uniformly distributed load of intensity small q over a simply supported span of length L, that is pre-stressed with a straight pre-stressing tendon or a pre-stressing cable, that is provided with a straight profile with the eccentricity E, therefore being constant, and thus resulting in a constant value E for the eccentricity function denoted as E with the argument x, which is therefore a constant value equal to, say, E in case of a straight profile for the pre-stressing tendon or the pre-stressing cable. Selecting the eccentricity E of the straight cable profile of the pre-stressing cable or pre-stressing tendon as equal to the overall depth D of the beam divided by 6 as shown in the figure depicting the pre-stressed concrete beam considered in the salt example presented in one of the earlier lectures. In other words, selecting the eccentricity E of the straight pre-stressing cable or pre-stressing tendon equal to 1/6 of the overall depth of the pre-stressed concrete beam by design, the necessary and sufficient condition that needs to be satisfied for the pre-stressed concrete beam to remain free of tensile stresses and thus remain uncracked is represented by equation number A, that is equation number capital A presented in one of the earlier slides, in the previous lectures, and equation A implies or requires that the normal bending stress denoted as sigma x at the extreme tension fiber of the pre-stressed concrete beam depicted in the figure in the salt example presented in an earlier lecture at the midspan of the pre-stressed concrete beam should be less than or equal to the cracking stress of concrete, that is, the cracking strength of concrete denoted as sigma subscript CR. which is the limiting condition for the pre-stressed concrete beam to remain uncracked. As specified by equation A in the previous lecture. For the special case where sigma CR, that is the cracking stress or cracking strength of concrete, denoted as sigma subscript CR, is specified as 0, the limiting condition represented by equation A will imply that the pre-stressed concrete beam is free of tensile stresses at all locations, since the normal bending stress at the critical location, that is the critical section, which is the midspan, represented by the coordinate x equal to 0, at the extreme tension fiber of the critical section, that is the midspan, represented by the y coordinate equal to minus d by 2, does not exceed the cracking stress of concrete specified as 0 in the salt example discussed in one of the earlier slides, based on the simply supported pre-stressed concrete beam subjected to uniformly distributed load denoted as Q, with a simply supported span length of L, as depicted by the figure in an earlier slide presenting the salt example in a previous lecture. Thus, assuming the cracking stress or the cracking strength sigma subscript CR of concrete equal to 0, signifying that the limiting condition that is specified by equation A will result in a pre-stressed concrete beam that is entirely in a state of compression or free from tensile stresses, and substituting the adopted or the specified value of the cracking stress of concrete sigma CR, that is equal to 0, into equation B, also presented in an earlier slide for the same salt example, representing the relationship for the normal bending stress sigma x at any general location, coordinates x and y, therefore result in a relationship between the internal tensile pre-stressing force in the steel, denoted as capital T subscript P, that will be required to achieve the limiting condition specified herein. And the requisite value of the pre-stressing tensile force in the pre-stressing steel, P, that is required to ensure that the pre-stressed concrete beam remains free of tensile stresses, is expressed by equation number 3, that can be derived in a straightforward manner by redistribution, rearranging the terms in equation number B after substitution of the limiting value of the cracking stress in equation number A. Further, noting that the cross-sectional area of the pre-stressed concrete beam is considered as B times D, that is the width times the overall depth. And therefore, given the prismatic rectangular cross-section of the pre-stressed concrete beam, the second moment of area, or the moment of inertia I subscript ZZ about the Z-axis for the pre-stressed concrete beam cross-section is BD cubed by 12. The ordinate or the height of the C line, that is the line of action of the internal compressive forces at end C above the coordinate axis X, that is the longitudinal coordinate axis of the pre-stressed concrete beam, or the central axis of the pre-stressed concrete beam, at the midspan, denoted as y over bar with argument 0, where 0 signifies the midspan or the cross section at the midspan at which x is equal to 0, may be calculated as d by 6, that is the overall depth, denoted as capital D divided by 6 for the pre-stressed concrete beam, presented in the solved example in an earlier lecture, with the design parameters consisting of the specified eccentricity of the straight pre-stressing tendon or pre-stressing cable as d by 6, and the cracking stress or the limiting value of the tensile stress at any location specified as 0. After determining the ordinate of the height y over bar of the C line, that is the line of action of the internal compressive forces at C, at the midspan, denoted as x equal to 0, we will proceed to the determination of the ordinate or height of the C line, that is the ordinate or height of the line of action of the internal compressive forces acting in the concrete, denoted as capital C, at other locations, for example, quarter span. Well, the further calculations are simpler since one can relate the externally applied bending moment mzq, that is denoted as capital M subscript Z superscript Q, representing the externally applied bending moment about the z-axis due to the external uniformly distributed load of intensity Q at any other location. For example, quarter spans represented by x coordinates plus minus L by 4 can be related to the externally applied bending moment M subscript Z superscript Q at the midspan, that is x equal to 0, by this relationship that is based on statics of the pre-stressed concrete beam considered as a simply supported beam supporting a uniformly distributed load of intensity Q over a simply supported span equal to L. Substituting the relationship into equations 2 and 3, the height or the ordinate of the C line, that is the internal compressive force resultant capital C at the quarter spans corresponding to x equal to plus minus L by 4 can be shown to be equal to the overall depth capital D divided by 12 by substitution and rearrangement of terms. Proceeding to the end spans for calculation of the ordinate or height of the C line, that is to locate and plot the locus of the C line or the line of action of the internal compressive forces at C along the span, that is along the x coordinate of the centroidal axis of the pre-stressed concrete beam, it is well known that the externally applied bending moment capital M subscript Z superscript Q due to the externally applied uniformly distributed load of intensity Q at the end spans represented by x equal to plus minus L by 2 are 0 for the simply supported conditions. That is, in case of the simply supported pre-stressed concrete beam with simple supports at the ends, the externally applied bending moment m subscript z superscript q at the end spans represented by x equal to plus minus L by 2 can be written as 0 or based on our engineering knowledge or statics of the pre-stressed concrete beam. Hence, substituting the value of the externally applied bending moment m subscript z superscript q into equation number 2, the ordinate or the height of the C line, that is the locus of the line of action of the internal compressive force resultant capital C in the concrete at the end spans represented by x coordinates equal to plus minus L by 2 would be simply equal to minus C based on equation number 2. After substitution of equation number 2 and 3, since the eccentricity of the straight cable or the straight pre-stressing tendon or cable denoted as E is equal to d by 6, the ordinate or the height of the C line at the midspan, that is x equal to plus minus L by 2, will be equal to minus d by 6. Applying the values of the ordinate or the height of the C line, that is the locus of line of action of the internal compressive forces resultant in the concrete, above the centroidal x-axis of the pre-stressed concrete beam as calculated in the present slide, one can plot the C line or the pressure and or thrust line, recognizing that the C line or the line of action of the internal compressive force resultant C in the concrete, in the pre-stressed concrete beam, should also follow a parabolic locus, as one can intuitively guess from equation numbers B and the results of the ordinates of the C line at the midspan, the quarter spans plus minus L by 4, and the end spans, that is x is equal to plus minus L by 2, derived in the present slide. In case of a curved cable profile, for example, a parabolic profile of the pre-stressing cable or tendon, the externally applied uniformly distributed load will again generate a parabolic C line, that is C line with a parabolic locus, since one can verify that the eccentricity function E with the argument x in case of a curved cable profile can be obtained by using the general polynomial equation for a parabolic cable profile or a parabolic function as equal to ax square plus bx plus c for the parabolic cable profile with the specific or specified coordinates, that is the eccentricity E at x equal to 0 or midspan, considered as the maximum eccentricity denoted as E subscript max at the midspan, that is x equal to 0, while the eccentricity E, that is found, calculated for the pre-stressing cable or pre-stressing tendon profile at the end spans represented by x equal to plus minus L by 2 found to be 0, one can obtain a mathematical or analytical solution for the C line, that is the plot of the line of action of the internal compressive forces at C in the concrete along the span length of the pre-stressed concrete beam, simply by rearranging the terms in question number 2. Thus resulting in the relationship between the ordinate or the height of the C line above the centroidal x-axis as equal to the externally applied bending moment divided by the internal pre-stressing force Tp in the pre-stressing cable. Noting that the functional variation of E argument x, that is the function E with the argument x, is a parabolic equation the cable profile of the pre-stressing cable has the same shape as the shape of the bending moment diagram, that is the externally applied bending moment m subscript z. It should be noted here that the similarity of the algebraic or polynomial functions describing the parabolic cable profile of the pre-stressing tendon or the pre-stressing cable are similar in fundamental nature to the functional variation of the externally applied bending moment, that is mz, along with the x-axis, simply because the function representing the cable profile, that is the profile of the pre-stressing cable or pre-stressing tendon along the x-axis, denoted as E with the argument x, can also be represented by an equation for a parabola, that is the functional variation of the eccentricity E with the argument x should also be examined to verify that the cable profile depicted by the eccentricity function E with the argument x resembles the shape of the bending moment diagram. Due to the externally applied tensile force, due to the externally applied uniformly distributed load. In case of a box girder, that is, in case the pre-stressed concrete beam is to be fabricated as a box girder, the second moment of area, denoted as I subscript ZZ, calculated using the simple formulation based on mechanics of materials, before we continue with our discussion on the elastic behavior of pre-stressed concrete beam elements or pre-stressed concrete flexural elements, and proceed to the elastic analysis of pre-stressed concrete beam using the C-line theory, let us list all the basic assumptions that we have inherently applied in locating the C line or the center of pressure line in case of the simply supported pre-stressed concrete beam subjected to a uniformly distributed load of intensity Q with a simply supported span L that was considered in the solved example presented in the previous slide. Now, the basic assumptions underlying the exercise of locating the C line or the center of pressure line for the simply supported pre-stressed concrete beam considered in the solved example in the previous slide may be summarized as 4 fundamental assumptions that are commonly employed in the elastic analysis of a pre-stressed concrete beam, in general subjected to uniaxial bending moments denoted as M subscript Z superscript Q due to the action of a uniformly distributed load of intensity Q in kilonewton per meter, for example. Therefore, the basic assumptions that were applied in the elastic analysis of the pre-stressed concrete beam considered in the solved example presented in the previous slide are as follows. 1. Both concrete and steel are assumed to remain linearly elastic prior to the cracking of concrete. That is, in the working range of loads or in the working stress range under working loads or service loads. As a result of this assumption of linear elastic behavior for both concrete and steel in the pre-stressed concrete beam prior to the cracking of concrete, allows the formulation of the following relationship between the normal bending stress sigma subscript x, where the subscript x signifies the direction of the normal stress, that is, the normal stress is in the longitudinal x direction along the centroidal axis of the beam at any general location of coordinates x and y with reference to the coordinate axis or the system, Cartesian system of coordinate axis that was adopted and illustrated in the figure for the pre-stressed concrete beam in one of the earlier slides, can be related to the normal strain denoted as epsilon x, that is epsilon subscript x, at any general location or the same general location or coordinates x and y by using the linear elastic relationship between the stress and the strain as expressed in equation number 1, that is Roman numeral 1. Therefore, the normal stress sigma x at coordinates x and y in general is equal to the modulus of elasticity of the concrete times the normal strain epsilon x at the same general coordinates. The second basic assumption that was employed in the determination of the C line or the center pressure line in case of the solid example presented in the previous slide, and in general the elastic analysis of a pre-stressed concrete beam subjected to uniaxial bending moments, is that plane sections before bending remain plane after bending. The necessary and sufficient condition for this assumption, that is assumption number 2 of plane sections remaining plane, is that the shear deformations in the beam are negligible. In other words, the shear strains are negligible in comparison to the flexural strains, as in case of a slender beam in which the plane sections before bending remain plane after bending, since the shear stresses in a slender beam are negligible in comparison to the normal bending stresses. Therefore, the plane sections before bending remain plane after bending in case of such slender beams if and only if the shear deformations are negligible in comparison to the flexural deformations, and therefore shear deformations can be ignored, thus resulting in the formulation of the following compatibility relationship, that is based on kinematics, expressing the compatibility of the normal strain epsilon x at any general coordinates x and y to the curvature of the beam element after bending as represented by the compatibility equation, that is equation number 2, that is Roman numeral 2. Using equations 1 and 2, or rather substituting from equation 2 to equation 1, one can derive the well-known or the classical relationship for the normal bending stress sigma subscript x at any general location x or y, x and y, with the uniaxial bending moment m subscript z superscript q, or in general m subscript z for any loading, concentrated loading or uniformly distributed loading, in terms of the moment of inertia or the second moment of area of the beam cross section about the ZZ axis and the coordinates x and y. The derivation of the classical or well-known relationship for the normal bending stress sigma x at any general coordinates x and y in case of a beam element subjected to a uniaxial bending moment can be found in all standard textbooks on mechanics, for example, textbooks by Irving Shames or R. Hibbler. The third basic assumption that has been inherently considered in the determination of the C line or the center of pressure line in case of the pre-stressed concrete beam considered in the solid example discussed in the previous slide is that long-term effects due to creep and shrinkage are negligible and ignored. The fourth assumption that is being employed in the solid example presented in the previous slide is characteristic of only pre-stressed concrete beams. It is worthwhile to note here that the first three assumptions, that is assumptions 1, 2 and 3, are common assumptions that are fundamental in nature and are valid for any beam element, regardless of whether the beam element is composed of reinforced concrete or pre-stressed concrete. In other words, the first three assumptions 1, 2 and 3 are common to both pre-stressed concrete beams as well as reinforced concrete beams for performing the elastic analysis of the beam. However, assumption number 4 is specifically valid for pre-stressed concrete beams only. That is, assumption number 4 is characteristic that is relevant or applicable only to pre-stressed concrete beams and not reinforced concrete beams. Therefore, assumption number 4 is valid or acceptable only for pre-stressed concrete beams and is not applicable to reinforced concrete beams, since assumption number 4 is based on the idealization that the change or increase in the internal pre-stressing force in the pre-stressing steel in case of the pre-stressed concrete beam, denoted as delta T subscript P, where the prefix delta signifies the change or the increase in the internal pre-stressing tensile force, while the notation T subscript P, as mentioned earlier, represents the internal pre-stressing tensile force in the steel that is transferred to the concrete after the pre-stressing operation and releasing of the pre-stressing steel. Thus, transferring the pre-stressing force from the steel to the concrete. And the assumption number 4 implies that the change or the increase in the internal pre-stressing tensile force in the steel in case of the pre-stressed concrete beam, delta Tp, during the flexural deformations or under the flexural or bending deformations, is negligible prior to the cracking of concrete. In other words, the change or increase delta Tp in the internal pre-stressing tensile force in the steel as well as concrete in the pre-stressed concrete beam due to the flexural or bending deformations are negligibly small. That is, prior to cracking of concrete only. Therefore, assumption number 4 is valid only for pre-stressed concrete beams and not reinforced concrete beams, and valid only prior to the cracking of concrete. Mathematically, the assumption number 4 can be expressed as delta Tp, that is the change or increase delta in the internal pre-stressing tensile force in the steel or concrete in the pre-stressed concrete beam, is much less than the original pre-stressing force Tp that is induced by the pre-stressing operation in the pre-stressing steel and subsequently transferred to the concrete at the time of transfer. Hence, by virtue of this assumption number 4, or the mathematical relationship or the mathematical representation of assumption number 4, the pre-stressing force, that is the internal tensile pre-stressing force in the concrete as well as the steel in case of the pre-stressed concrete beam, can be assumed to be more or less constant prior to the cracking of concrete, even when the pre-stressed concrete beam undergoes flexural or bending deformations. The pre-stressing force that is the internal pre-stressing tensile force in the steel and the internal pre-stressing compressive stresses in the concrete remain constant for all practical purposes, even under the flexural bending or during the flexural or bending deformations of the beam due to the application of the uniaxial bending moment. And thus, the internal pre-stressing tensile force in the pre-stressing steel, in case of the pre-stressed concrete beam, can be assumed to be constant and equal to the original pre-stressing tensile force Tp, that is induced by the pre-stressing operation. Well, based on these assumptions, we can now proceed to the attempt of the solution for assignment number 2 by following the guidelines presented in the solved example in the earlier slides for performing the elastic analysis of the pre-stressed concrete beam or the pre-stressed concrete box girder, that is a girder or a beam with a box section that is presented in question number 1 of assignment number 2, which is pre-stressed with 2 cables or tendons as shown in this schematic figure for the box section of the pre-stressed concrete box girder considered in question number 1 of assignment number 2. The box section is provided with 2 pre-stressing cables or tendons, one in each web of the box section, to achieve symmetry not of the beam cross section on the box section, not only symmetry in terms of the geometry, but also symmetry in the uniaxial bending response of the pre-stressed concrete beam. In other words, the pre-stressed concrete beam or the box girder with the box section is provided with 2 pre-stressing cables, one in each web of the box section, so that the pre-stressed concrete box girder undergoes symmetrical uniaxial bending about the z-axis, that is the major axis of the beam cross section. And as given in the data for question number 1 in assignment number 2, the total pre-stressing force in the 2 cables is specified as Tp equal to 9,000 kilonewton, which implies that the sum total of the pre-stressing force in the two pre-stressing cables or tendons, that is one pre-stressing cable or tendon provided in each web of the box section, is 9,000 kilonewton. And since the pre-stressing cables or tendons, and therefore the pre-stressing force in each cable is symmetrical about the minor axis YY of the beam cross section of the pre-stressed concrete box girder beam, the pre-stressed concrete beam or the pre-stressed concrete box girder considered in question number 1 of assignment number 2 undergoes symmetrical uniaxial bending about the major axis ZZ of the beam cross section. Thus, for simplification in the elastic analysis of the pre-stressed concrete beam, one can idealize the box section of the pre-stressed concrete box girder, that is in practice box section illustrated in this figure, with idealization of the box section as an equivalent rectangular section or an equivalent I section with the equivalent flange areas and web areas in case of the I section, or equivalent moment of inertia of the second moment of area and the cross-sectional area in case of idealization as a rectangular section, pre-stressed with one single equivalent cable with the effective pre-stressing force in the single or equivalent pre-stressing cable in the idealized cross-section equal to 9,000 kilonewton. We will discuss more about this idealization of the pre-stressed concrete beam or the pre-stressed concrete box girder cross-section, that is in reality a box section but idealized as an equivalent rectangular section or an equivalent I section with representative geometric properties assigned to the equivalent rectangular section that are based on the geometric properties of the original box section. When we continue with our discussion on the methodology of solution of question number 1 in assignment number 2 and perform the elastic analysis of the pre-stressed concrete beam based on the fundamental assumptions 1, 2, 3 and 4 discussed in the present slide. In this context, one may recall, as presented in the previous slide, that the equivalent moment of inertia or second moment of area of a box section about the major axis ZZ of the box section that may be assigned to the idealized equivalent rectangular cross section is simply calculated as the moment of inertia of the outer rectangle minus the moment of inertia of the inner hollow rectangle, and the equivalent cross-sectional area of the box section that may be assigned to the idealized equivalent rectangular section for purposes of elastic analysis of the pre-stressed concrete box girder is simply calculated as the area of the outer rectangular minus the area of the inner rectangle corresponding to the hollow part of the box section. Therefore, assigning the representative geometric properties of the box section, such as the representative moment of inertia or the second moment of area about the major axis ZZ, and the area of cross section of the box section to the equivalent rectangular section, the elastic analysis of the pre-stressed concrete beam will be performed based on the fundamental assumptions 1, 2, 3, and 4 listed in the present page, the present slide, for the purposes of illustrating the methodology of the solution to question number 1. Continuing our discussion on the methodology for the solution of question number 1 of assignment number 2 presented in an earlier slide, we idealize the box girder, that is the pre-stressed concrete beam with a box type cross section, and thus classified as a pre-stressed concrete box girder in the terminology of structural elements, as an equivalent rectangular section or an equivalent I section that is assigned with equivalent geometric properties that are representative of the original pre-stressed concrete box girder. Essentially, the solution to question number 1 of assignment number 2 presented in an earlier slide can be completed by assigning representative equivalent geometric properties. For example, the second moment of area or the moment of inertia IZZ about the major axis of the box section of the pre-stressed concrete box girder calculated as the moment of inertia or the second moment of area of the outer rectangle minus the moment of inertia or the second moment of area of the inner rectangle, that is the hollow part of the pre-stressed concrete box girder section. While assigning an equivalent representative cross-sectional area denoted as A of the given pre-stressed concrete box girder section calculated as the area of the outer rectangle minus the area of the inner rectangle, that is the hollow part of the pre-stressed concrete box girder section to the idealized equivalent I section or rectangular section. Further, replacing the two pre-stressing cables or tendons provided in each web, that is one pre-stressing cable or tendon provided in each web of the pre-stressed concrete box girder section for purposes of symmetry in the geometrical properties as well as the symmetry in the uniaxial bending or flexural response of the pre-stressed concrete box girder. Idealizing or replacing the two pre-stressing cables or tendons, that is one cable or tendon in each web of the original box girder section with a single pre-stressing cable having the same parabolic profile described by the eccentricity function E with argument x, signifying that the eccentricity function of the parabolic cable profile of the equivalent single pre-stressing cable is a function of the coordinate x and idealizing that the total pre-stressing force in the two pre-stressing cables or tendons provided in the two webs respectively of the original pre-stressed concrete box girder section can be substituted or replaced by a total pre-stressing force Tp that is the effective pre-stressing force Tp given in question number 1 of assignment number 2 as the sum total of the pre-stressing force or pre-stressing forces in the two pre-stressing tendons or cables in case of the original box girder section. Based on the above mentioned idealizations, we can now proceed with the discussion on the methodology of solution for question number 1 of assignment number 2, beginning with the part 1 of question number 1 of assignment number 2 presented in the previous slide. The distribution of the normal stress sigma x along the depth of the cross section of the pre-stressed concrete beam that is presented in question number 1 of assignment number 2 at the three cross sections or locations of interest, that is x equal to 0 corresponding to the mid-span section, x equal to plus minus L by 4, that is the cross section at the quarter spans, and x equal to plus minus L by 2, that are the coordinates of the cross sections of the pre-stressed concrete beam at the end spans with reference to the coordinate axis or the Cartesian system of coordinate axis illustrated in the figure of the pre-stressed concrete beam in the solved example presented in one of the earlier lectures. Hence, the normal stress sigma x at any general location or coordinates x and y in the pre-stressed concrete beam can be calculated using equation number B presented for the salt example in one of the earlier lectures. While enforcing the limiting condition specified in question number 1 of assignment number 2, that is the normal stress sigma x at the extreme tension fiber at the midspan section of the pre-stressed concrete beam does not exceed the limiting value specified in the question statement of question number 1 of assignment number 2. Therefore, applying equations B with substitution of the limiting value of the normal stress sigma x considered in equation number A in case of the salt example presented in one of the earlier lectures, we can compute the distribution of the normal stress at the 3 locations or cross sections of interest in case of the pre-stressed concrete beam considered in question number 1 of assignment number 2. Using equation B from the salt example that was presented in an earlier slide in one of the previous lectures. Proceeding to the methodology of solution for part B of question number 1 of assignment number 2, wherein we are required to locate and plot the C line for the pre-stressed concrete beam considered in question number 1 of assignment number 2. One can refer to the salt example presented in the previous slide based on the determination of the C line for a pre-stressed concrete beam with a rectangular cross section simply by applying the statical equilibrium equations 1 and 2 that are presented in the salt example in a previous lecture for determining the locus or the path of the line of action of the C line that is the locus of the internal compressive force resultant in the concrete, in case of the pre-stressed concrete beam, considered in the salt example. Equation B, as one can observe, presented in the salt example in one of the earlier slides, provides the relationship for the ordinate or the height of the C line, that is the locus of the internal compressive force resultant in the concrete in a pre-stressed concrete beam subjected to a uniformly distributed load that is simply supported over a span of length L, in terms of the bending moment or the uniaxial bending moment function m subscript z superscript q with the argument x, the pre-stressing force in the pre-stressing steel after transfer, Tp, that is capital T subscript P, and the eccentricity function that characterizes the cable profile of the pre-stressing tendon or the cable in general, represented by the function E with the argument x. Changing the terms in the equation number B, that is the moment equilibrium about the major axis ZZ of the pre-stressed concrete beam, one can obtain the analytical solution or the analytical function for the ordinate or height of the C line, denoted as y over bar with the argument x, in terms of the uniaxial bending moment function m subscript z superscript q with the argument x, and the eccentricity function E with the argument x, resulting in the solution of the part 2 of question number 1 of assignment number 2, that requires the determination of the C line or the locus of the internal compressive force resultant in the concrete due to the combined action of the externally applied uniformly distributed load of intensity Q, as well as the pre-stressing force T subscript P in the pre-stressing steel after transfer. Continuing with our discussion on the methodology of solution of question number 1 of assignment number 2, note that the methodology of solution for question number 2 of assignment number 2, that is the second question of assignment number 2, was already presented and discussed with a solved example in one of the earlier lectures. Hence, in the present slide, we are discussing the methodology of solution to parts 1, 2, that is parts 1 and 2 of question number 1 of assignment number 2. In the third part, that is part 3 of question number 2 of, rather, question number 1 of assignment number 2, part 3 requires the elastic analysis of the pre-stressed concrete beam presented in question number 1 of assignment number 2 using the C-line method of elastic analysis, also referred to as the internal resisting couple method of elastic analysis of pre-stressed concrete beams. The theoretical basis for the internal resisting couple method of elastic analysis, or the C-line method of elastic analysis of pre-stressed concrete beams, lies in the moment equilibrium equation, that is equation B, of a general cross-section X in a pre-stressed concrete beam based on the fundamental assumptions enumerated in one of the earlier slides. As a brief theoretical background, the background information or background theory for the internal resisting couple or C-line method of elastic analysis of pre-stressed concrete beams considering the moment equilibrium equation, that is equation B, for a general cross-section located at ordinate X of the pre-stressed concrete beam considered in the solved example, for a zero external moment, that is the externally applied bending moment due to the external uniformly distributed load denoted as m subscript z superscript q with a function argument x equal to 0, as in case of the simply supported ends of the pre-stressed concrete beam, the C line coincides with the line of action of the internal pre-stressing tensile force Tp in the pre-stressing steel. And the physical reasoning or the physical explanation for this phenomenon is intuitive, as one can intuitively visualize that the C line or the locus of the line of action of the internal compressive force resultant in the concrete must coincide with the line of action of the internal pre-stressing tensile force Tp in the steel in order to satisfy the moment equilibrium equation, that is equation B, presented in one of the earlier slides. In other words, since the bending moment, that is the externally applied bending moment due to the external uniformly distributed load, denoted as m subscript z superscript q, at any coordinate or location x, being equal to 0, as in case of the simply supported ends of the pre-stressed concrete beam, the internal resisting couple, that is defined in the moment equilibrium equation B, must also be equal to 0 in order to satisfy the moment equilibrium at the cross section or where the externally applied bending moment is 0. Hence, at such cross sections where the externally applied bending moment m subscript z superscript q is 0, as in case of the simply supported ends of the pre-stressed concrete beam, the C line must coincide with the pre-stressing tensile force Tp in order to satisfy the moment equilibrium equation B. As the internal resisting couple has to be equal and opposite to the externally applied bending moment at all cross sections or locations X of the pre-stressed concrete beam. Further, as the externally applied bending moment M subscript Z superscript Q as a general function of the ordinate X increases along the span of the pre-stressed concrete beam, the C line, that is the locus of the internal compressive force resultant in the concrete, has to shift from the line of action of the internal pre-stressing tensile force Tp in the pre-stressing steel by distance or height or a separation that is equal to the internal lever arm denoted as A small a with the argument x, signifying that the internal lever arm small a is a function of the ordinate x of the internal resisting couple at the location x as defined in the moment equilibrium equation B presented in the earlier slide in one of the previous lectures. The shift in the line of action or the C line, that is the locus of the internal compressive force resultant in the concrete, from the pre-stressing steel can be calculated, therefore, from the moment equilibrium equation 2 as depicted in equation number 4, thus resulting in the ordinate or height of the C line above the centroidal axis X of the pre-stressed concrete beam, that is denoted as Y over bar X, as represented in equation number 4. The analytical solution therefore of the stress distribution based on the C line concept or the internal resisting method of elastic analysis may be expressed by relating the normal bending stress sigma x at any location xy of the pre-stressed concrete beam to the internal compressive force resultant in the concrete, denoted as capital C, and the ordinate or the height of the C line above the centroidal axis x, denoted as Y over bar X, in terms of the cross-sectional area A and the second moment of area or the moment of inertia IZZ about the major axis of the pre-stressed concrete beam cross-section, and the ordinates X and Y. Noting that the internal compressive force resultant C in the concrete is equal to the internal pre-stressing tensile force Tp in magnitude based on the force equilibrium equation, that is equation number 1, for any general cross-section X of the pre-stressed concrete beam. One can replace the internal compressive force resultant C with the internal pre-stressing tensile force Tp in the relationship for the normal bending stress presented herein based on the internal resisting couple or the C-line method of elastic analysis, thus resulting in a compact form of the relationship of the normal bending stress at any location xy of the pre-stressed concrete beam in terms of the internal tensile pre-stressing force Tp in the pre-stressing steel, the ordinate or height y over bar of the pre-stressing force above the central axis of the pre-stressed concrete beam, the cross-sectional area A of the pre-stressed concrete beam, and the moment of inertia for the second moment of area IZZ about the major axis of the pre-stressed concrete beam, and the coordinates X and Y as expressed in equation number 5. It is worthwhile to mention here that equation number 5 is simply an alternative form of equation number B for the normal bending stress at any location X and Y, and can be shown to be or derived by simply rearranging the terms in equation number B for the normal bending stress that was presented in an earlier slide in one of the earlier lectures, by substituting the moment equilibrium equation, that is equation 2, presented in the salt example in an earlier lecture, into equation number B for the normal bending stress, also presented in one of the earlier lectures. However, the alternative form of the relationship presented by equation number 5 for the normal bending stress is a more compact form and provides an alternative physical interpretation of the normal bending stress in a pre-stressed concrete beam, that is the cause of the normal bending stress is illustrated by equation number 5. In other words, equation number 5 for the normal bending stress in terms of the internal compressive forces resultant C is based on the effect of the pre-stressing tensile force Tp, while the original form of the relationship for the normal bending stress sigma x, that is presented by equation B, depicts the normal bending stress at any general location x and y of the pre-stressed concrete beam in terms of the cause of the normal bending stress, that is the externally applied bending moment m subscript z superscript q, and the pre-stressing tensile force Tp, while equation 5 depicts the normal bending stress in terms of the internal compressive forces resultant C in the concrete and the ordinate of the C line y over bar, which are both effects of the pre-stressing, thus presenting an alternative perspective for the physical interpretation of the effect of pre-stressing on the normal bending stress. However, one should note or remember that equation 5 and equation B, representing the relationship for the normal bending stress sigma x at any general coordinates x and y, are equivalent equations, and one can be either one of equation B or equation number 5 can be rearranged to arrive at the other equation by substituting the moment equilibrium equation, that is equation number 2, or using the internal resisting couple or the C line concept. Before proceeding to our discussion on the methodology of solution of part D of question number 1 in assignment number 2, that is based on the load balancing concept, in pre-stressed concrete beams, let us first summarize the results of our mathematical derivations or formulations that were presented in the previous slides as part of the solution of question number 1 of assignment number 2 in terms of a closed form analytical solution of the C line that depicts the essence of the C line theory as well as the elastic performance of pre-stressed concrete beams in a nutshell, in the form of fundamental equations presented herein, which represent the closed form analytical solution of the C line. Well, noting that the mathematical function describing the variation of the externally applied bending moment due to the external uniformly distributed load denoted as M subscript Z superscript Q with the functional argument X in case of a pre-stressed concrete beam that is simply supported and subjected to a uniformly distributed load of intensity Q may be expressed by this equation, wherein M, the notation M at 0, that is notation M with the argument 0, representing the bending moment at the midspan of the coordinate x equal to 0, in terms of the coordinate axis illustrated in one of the earlier slides for the pre-stressed concrete beam considered in the solid example presented in an earlier lecture. Well, as we are all aware, the mathematical function or the closed form analytical solution for the externally applied bending moment M subscript Z superscript Q as a function of the ordinate x is a parabolic function or a quadratic function that is presented in this equation here. Further noting that in case of a parabolic cable profile, that is cable profile of the pre-stressing tendon of the cable represented by the eccentricity function, that is a parabolic function or a quadratic function presented herein, where the notation E subscript 0 denotes the maximum eccentricity of the parabolic cable profile with respect to the centroidal axis x of the pre-stressed concrete beam at the midspan, that is the coordinate x equal to 0. Recall that the moment equilibrium equation, that is equation number 2, relating the externally applied bending moment m subscript z superscript q to the internal resisting couple formed by the internal compressive force resultant in the concrete and the pre-stressing tensile force in the pre-stressing steel was derived as this equation substituting the values or the relationships for the externally applied bending moment m subscript z superscript q and the eccentricity function E with the argument x into the equation or the relationship for the ordinate y over bar x of the C line, one can obtain the mathematical relationship for the ordinate or the height y over bar of the C line at any general coordinate x in terms of the externally applied bending moment, the internal pre-stressing tensile force in the steel, and the eccentricity function E with the argument x as represented in this closed form analytical solution of the C line. Having derived the closed form analytical solution of the C line as represented by this equation that is tick marked, we can substitute the ordinate or the height denoted as y over bar with the argument x of the C line above the centroidal axis x as obtained in this equation into equation number 5 to calculate the distribution of the normal bending stress sigma x at any general coordinates x and y of the pre-stressed concrete beam based on the C-line theory and the internal resisting method or the C-line method of elastic analysis of the pre-stressed concrete beam. Continuing our discussion on the methodology of solution for question number 1 of assignment number 2, as mentioned earlier, the part 4 or part D rather, of question number 1 in assignment number 2 is based on the load balancing concept in pre-stressing beams. As a brief theoretical background to the load balancing concept, one can intuitively visualize that different cable profiles will induce different types of reactions between the cables and the concrete. For example, a straight pre-stressing cable profile, as illustrated in this figure, will induce concentrated horizontal reactions at the end of the pre-stressed concrete beam. A triangular cable profile displayed in this figure will induce concentrated inclined reactions in the pre-stressed concrete beam at the two ends, as well as a concentrated reaction at the point of the turning of the pre-stressing cable or the pre-stressing tendon, denoted as capital R subscript P, which will act along the line bisecting the triangular cable profile. Further, a trapezoidal cable profile, such as the one shown in this figure, will induce two concentrated reactions denoted as capital R subscript P between the pre-stressing cable and the concrete, acting at the vertices, the turning points of the trapezoidal cable profile, in addition to the concentrated reactions at the ends of the cable profile or the pre-stressed concrete beam. Continuing or extrapolating the argument, a curved cable profile, therefore, that in principle has infinite number of turning points. For example, a parabolic cable profile, as illustrated in this figure, will induce a uniformly distributed reaction, that is denoted as small r subscript p, between the pre-stressing cable and the concrete, normal to the cable profile. In the pre-stressed concrete beam with a parabolic or curved cable profile. In a sense, the cable profile that is selected for a given pre-stressed concrete beam for the specified loading should be such that the cable profile generates a system of reactions denoted as capital R subscript P or small r subscript P, that is concentrated reactions capital R subscript P, or uniformly distributed reaction small r subscript P, that counteracts the external loads. For example, the concentrated load or the point load, or the UDL, for example, the uniformly distributed load Q, or even balance the external loading in principle. As examples, the triangular cable profile illustrated in this figure generates a concentrated reaction capital R subscript P that counteracts a concentrated load capital Q acting at the midspan of the pre-stressed concrete beam, while the trapezoidal cable profile pre-stressed to a pre-stressing force capital T subscript P in this figure induces a system of reactions consisting of two concentrated loads or point loads denoted as capital Q, rather R subscript P, capital R subscript P, that counteract the applied concentrated loads denoted as capital Q, or even balance the applied concentrated loads. while the curved or the parabolic cable profile presented in this figure produces a system of reactions between the cable and the concrete consisting of a uniformly distributed reaction denoted as small r subscript p that should in theory counteract or even balance an externally applied uniformly distributed load small q. Hence, qualitatively, the cable profile in a prestressed concrete beam in principle can be selected to produce a system of reactions between the cable and the concrete, which may consist of concentrated reactions such as capital R subscript P or uniformly distributed reaction denoted as small r subscript P, or a combination of both, that will counteract the externally applied loading. For example, concentrated external loads denoted as capital Q or uniformly distributed external loads denoted as small q, or even balance the external loads in principle. Further, in general, the pre-stressing force capital T subscript P in the pre-stressing cable or tendon will balance the external loads if the cable profile follows the shape of the bending moment diagram that is described by the function m subscript z superscript q produced by the external loads q as intuitively interpreted from these figures. One can conclude based on the physical interpretation of the effect of the reactions induced by the different cable profiles between the cable and concrete, the most appropriate cable profile that will balance or counteract the external loads is the one that follows the shape of the bending moment diagram that is produced by the external loads, capital Q or small q. Considering the case of the precessed concrete beam shown in this figure, subject to concentrated or point loads acting at 1/3 points of the precessed concrete beam, a trapezoidal cable profile can, in principle, balance the externally applied concentrated transverse loads, capital Q, since the trapezoidal cable profile follows the shape of the bending moment diagram that is produced by the third point concentrated transverse loading as depicted in this figure by the bending moment diagram illustrated in green ink. Continuing our discussion on the theoretical basis and methodology for the solution of part 4 or part D of question number 1 of assignment number 2, based on the concept of load balancing, recall that by definition the load balancing is achieved, that is, the external loading acting on a pre-stressed concrete beam is considered to be balanced when the externally applied bending moment m subscript z superscript q due to the externally applied load or external loading, for example, the UDL or the uniformly distributed load denoted as Q, is completely counteracted and nullified at all locations, that is, at all cross sections or sections X of the pre-stressed concrete beam by the virtue of the pre-stressing force. Qualitatively, in general, the externally applied load or the external loading on a pre-stressed concrete beam is balanced or counteracted when the shape of the cable profile, that is, the cable profile of the pre-stressing cable, follows the shape of the bending moment diagram that is induced by the external loading Q in the pre-stressing beam along the span of the pre-stressed concrete beam. the mathematical proof of the load balancing concept, that is, the mathematical proof of the statement of load balancing can be obtained very conveniently using the C-line theory. Based on the C-line theory, the pre-stressing force Tp in the pre-stressing cable or tendon balances the external load, for example the UDLQ in case of the simply supported pre-stressed concrete beam subjected to a uniformly distributed load of intensity Q, if and only if the ordinate or the height of the C line, denoted as y over bar the argument x, expressed as a function of x, is 0 at all locations, that is, at all cross sections of the pre-stressed concrete beam for all values of x. In physical terms, the mathematical condition, wherein the ordinate or the height y over bar x of the C line is equal to 0 for all x or all cross sections x, implies that the C line coincides with the centroidal axis of the beam at all cross sections, that is, for all values of x, and hence one can mathematically show that all the cross sections x in the pre-stressed concrete beam are in a state of pure uniform axial compressive stress as depicted in this figure, by applying equation number B for the normal stress in the pre-stressed concrete beam that was presented in one of the earlier slides. And hence the pre-stressed concrete beam in which the load is balanced by satisfying the mathematical condition, that is y over bar as a function of x is 0 for all values of x, is in a state of pure axial compression and is free from bending stresses or bending moments. Proceeding with the mathematical proof of the load balancing concept, substituting the mathematical condition that requires the ordinate height y over bar x of the C line at any general location or general X is equal to 0 into equation number 4 presented in the previous slide, the equation number 4 provides the relationship between the cable profile function, that is the function that describes the cable profile, with the bending moment function, that is function that describes the variation of the bending moment due to the external loading Q along the span of the beam, that is along the X coordinate, resulting in the required cable profile function that is needed for achieving the load balancing. Rearranging the terms in equation number 4 for a zero value of the ordinate or height y over bar at any x, the cable profile function that is required for achieving load balancing or balancing the externally applied load in a pre-stressed concrete beam is expressed by equation number 6, which implies that the cable profile function, or the function that describes the cable profile of the pre-stressing steel cable or steel tendon, denoted as E, signifying the eccentricity of the cable profile with respect to the centroidal axis of the pre-stressed concrete beam, subscript BAL, where the subscript BAL signifies that the eccentricity of the cable profile, or the cable profile itself, is the one required for achieving the load balancing condition, with the argument X is found to be equal to the ratio of the bending moment function, that is the function that describes the variation of the externally applied bending moment M subscript Z, that is the bending moment about the major axis ZZ of the pre-stressed concrete beam, superscript Q, which signifies that the bending moment is due to the externally applied load or the external loading, for example the UDL of intensity Q, with the argument X divided by the pre-stressing force Tp in the pre-stressing cable or tendon. To summarize, therefore, based on the C-line theory, it can be mathematically proven that the pre-stressing force Tp in the pre-stressing cable or tendon balances the external load if the cable profile function satisfies equation number 6, which in physical terms implies that the cable profile follows the shape of the bending moment diagram, that is induced by the externally applied load. In other words, a cable profile will counteract or even balance the external load if and only if the cable profile follows the shape of the bending moment diagram that is induced by the external loading Q, as represented mathematically by equation number 6. Equation number 6, that is the necessary and sufficient condition for achieving load balancing, is also the necessary and sufficient condition for achieving a uniform compressive stress distribution at all the locations in the beam, that is a state of pure axial compression at all the cross sections in the beam, or at all sections x for all values of x. And the mathematical proof of the necessary and sufficient condition just stated is that substituting the cable profile function that is required for achieving load balancing, for balancing the external load provided by equation 6, into equation number 4 presented in the previous slide, the ordinator height h can be shown to be equal to 0 for the C line at all locations. That is, for all values of x, the C line coincides with the centroidal axis of the pre-stressed concrete beam at all cross sections, which, based on equation number 5 presented in the previous slide implies that the normal stress at any general location or coordinates x and y in case of a beam, that is a pre-stressed concrete beam in which the cable profile satisfies the cable profile function that is required for load balancing presented in equation number 6, and therefore the C line coincides with the centroidal axis of the pre-stressed concrete beam at all locations or all values of x, resulting in a uniform axial compressive stress at all local locations or coordinates x and y on substitution into equation number 5 presented in the previous slide. Thus, in conclusion, load balancing is achieved, or the external load acting on the pre-stressed concrete beam is considered to be balanced when the external bending moment mzq is balanced or completely counteracted by the pre-stressing force Tp at all locations or at all cross sections x of the beam, and the mathematical proof of the definition of load balancing just stated is conveniently derived based on the C-line theory, which implies that the pre-stressing force Tp in the cable or tendon will balance the external load if and only if the ordinate or the height y over bar x of the C line above the centroidal axis of the beam equals 0 for all values of the x, or the C line coincides with the centroidal axis of the pre-stressed concrete beam at all locations x, that is for all values of x. Back substituting this condition, that is the necessary and sufficient condition y over bar x equal to 0 for all x back into equation number 4, one can mathematically show that the cable profile function, or the cable profile that is required to achieve load balancing, is given by equation number 6. Further, substituting the necessary and sufficient mathematical condition, that is y over bar x equal to 0, into equation number 5, also presented in the previous slide as equation number 4, results in the relationship for the normal stress at any general location or coordinates x and y in the pre-stressed concrete beam in which the load is balanced. And the resulting equation for the normal stress sigma x at any location x and y for the condition of load balancing is a uniform axial compressive stress equal to minus Tp divided by A, thus implying that the pre-stressed concrete beam in which load is balanced, or the condition of mathematical condition for load balancing is fulfilled, is in a state of pure uniform axial compressive stress. Since the C line coincides with the centroidal axis of the pre-stressed concrete beam at all locations x, or at all cross sections x, for the mathematical condition of load balancing, that is, the C line and the centroidal axis of the pre-stressed concrete beam are collinear or coincident, in case the necessary and sufficient mathematical condition for load balancing is fulfilled and the cable profile balances the external load by satisfying equation number 6 for the cable profile function that is required to achieve load balance. In conclusion to our discussion on the elastic behavior of pre-stressed concrete beams, or PSC beams, that is pre-stressed concrete flexural elements, let us summarize the comparison of the elastic flexural behavior of pre-stressed concrete beams versus corresponding reinforced concrete beams based on the C-line concept in the range of working loads or service loads, that is, in the working stress range under working loads or service loads. The fundamental differences between the elastic flexural behavior of PSC beams in comparison to corresponding RC beams are summarized in a tabular format in the present slide. And as listed in the table presented in the current slide, the first fundamental difference between the elastic flexural behavior of a pre-stressed concrete beam versus a corresponding reinforced concrete beam is that in case of the pre-stressed concrete beam, the variation in the external moment, denoted as M subscript Z superscript Q, as a function of X, signifying the variation of the external moment M subscript Z superscript Q along the X coordinate or the longitudinal centroidal axis of the beam under the action of the external loads results in a corresponding variation in the ordinate or the height y over bar x, that is the ordinate or the height y over bar is a function of x signified by the argument x of the C line, that is also the ordinate or the height of the internal compressive force resultant C of the internal compressive forces in the concrete, which by the requirement of statical force equilibrium for any section should equal the internal tensile force in the pre-stressing steel, that is T subscript P, at all locations or coordinates X of the pre-stressed concrete beam. In contrast, in a reinforced concrete beam, the variation of the external moment M subscript Z superscript Q due to the external loading along the span of the beam results in a change or variation in the internal force resultants C, that is the internal compressive force resultant C of the compressive stresses in the concrete, as well as variation in the internal tensile force resultant, that is the internal tensile force in the reinforcing steel, denoted as capital T subscript S, where the notation capital T signifies tensile force in the reinforcing steel, while the subscript S signifies the reinforcing steel, and the argument X signifies that the internal compressive force resultant C in the concrete as well as the internal tensile force resultant in the reinforcing steel T subscript S are both functions of X. Since the internal force resultant C and T, that is the internal compressive force resultant in the concrete and the internal tensile force resultant due to the pre-stressing force in the pre-stressing steel Tp are more or less constant along the span, thus dropping the argument X, the internal compressive force resultant C in the pre-stressed concrete beam is a constant and is equated or equal to the internal tensile force in the pre-stressing steel, or the pre-stressing force in the pre-stressing steel denoted as T subscript P. As a result, the internal lever arm defined in one of the earlier lectures and denoted as A, which in general is a function of X, that is signified by the argument X, must vary in case of the pre-stressed concrete beam along the span or the longitudinal coordinate, that is the centroidal axis X of the pre-stressed concrete beam, in order to accommodate the variation of the bending moment, that is the externally applied bending moment due to the external loading M subscript Z superscript Q, simply because the internal compressive force resultant C, that is the force resultant of the internal compressive stress distribution in the concrete in case of the pre-stressed concrete beam, is constant along the length or the span, that is the centroidal or the longitudinal axis X of the beam, and is equal to the pre-stressing force, that is the internal tensile pre-stressing force in the pre-stressing steel Tp. In contrast, in case of a reinforced concrete beam, since the internal lever arm represented by the same notation as in case of the pre-stressed concrete beam, that is A of the internal resisting couple formed by the internal compressive force resultant and the internal tensile force resultant. is more or less constant along the span in case of the reinforced concrete beam, and the internal lever arm is governed or dictated or determined by the material properties of the cracked reinforced concrete section. The internal force resultants, that is the internal compressive force resultant in the concrete, as well as the internal tensile force resultant, that is the internal tensile force in the reinforcing steel, must vary along the span to accommodate the variation of the external bending moment due to the externally applied loading. Simply because the internal lever arm A, which in general is a function of x, signified by the argument x, is more or less constant along the span of the reinforced concrete beam and is calculated as JD in the notation of the working stress method of analysis of reinforced concrete beams, where JD is more or less a constant and is equal to the internal lever arm between the internal compressive force resultant in the concrete and the internal tensile force in the reinforcing steel in case of the reinforced concrete. And the internal lever arm of the internal resisting couple formed by the internal compressive force resultant in the concrete and the internal tensile force resultant due to the tensile force in the reinforcing steel in case of the reinforced concrete section is dictated by the material properties of the cracked concrete section and generally determined to be more or less constant along the span x of the reinforced concrete beam.